Picture two objects at the top of a ramp, a rectangular block and a solid cylinder. They have the exact same mass. We let them go. The block slides down, while the cylinder rolls. To understand how they move, we must look at them as rigid bodies. A rigid body is a physics model for a system of particles where the physical distance between any two internal points never changes, no matter the force applied. This diagram shows the sliding block. This block is in pure translation. That means every single particle inside of it is moving in the exact same direction, at the exact same speed, simultaneously. Now look at the diagram of the rolling cylinder. Its internal particles are moving at completely different speeds. The particles near the top are moving much faster than the particles near the center. Even stranger, if you measured the exact point where the cylinder touches the ramp, its instantaneous velocity is 0. It isn't moving forward at all in that split second. That stationary point proves the particles aren't traveling uniformly. Because the particles inside the rolling cylinder are moving at all these varying speeds, its overall movement has to be a combination. It is undergoing pure translation, but it is also exhibiting a secondary distinct mechanical behavior at the exact same time. To figure out what that secondary motion is, we need to eliminate translation entirely. We do that by taking a rigid body and physically pinning it in place. You see constrained objects like this every day, a ceiling fan fixed to your roof or a potter's wheel mounted to a table. Because they are restricted, they can only move in one specific way. If you fix a specific point on the object, it can't travel across the room. Its motion is completely restricted to either oscillating back and forth or spinning entirely around that pivot. This brings us to pure rotation. Pure rotation occurs when a body moves around a single, immovable straight line, rather than just pivoting on a single point. We call that straight line the axis of rotation. In the real world, axes can wobble, like a spinning top losing momentum as it hits the floor. But to isolate the fundamental physics, we require an axis that is strictly fixed in place. By logging that axis in place, we create a mechanical environment where translation is mathematically impossible. We have successfully isolated pure rotation. Let's dive inside a spinning rigid body and track the specific trajectory of just one single internal particle. This diagram outlines the exact geometric path of that particle. It forms a perfect circle that is strictly perpendicular to the fixed central axis. The radius of that specific particle's circular path is determined entirely by its perpendicular distance from the rotational axis. The further out the particle is, the wider the circle it draws. But what if a particle is located exactly on the axis itself? Its distance from the center is 0, meaning its circular path has a radius of 0. That's why its velocity remains absolute 0 while the rest of the body spins around it. Even though their linear speeds vary, all these moving particles share one metric: angular velocity. Angular velocity is the rate at which an object rotates relative to another point, measured in angles over time. Every single particle in the rigid body shares this exact same rate of rotation. Pure rotation means whether a particle is an inch from the center or a foot away, they all complete one full rotation in the exact same amount of time. They share the same angular velocity, even though their physical distance from the axis makes their linear speeds drastically different. We can now return to the rolling cylinder on the ramp, equipped with the mechanical rules for both pure translation and pure rotation. This diagram shows a body undergoing only pure translation. Its internal trajectories are simple. Every point inside it traces identical, straight, parallel lines. But when a body combines translation and rotation, those internal trajectories change shape entirely. The center point still moves in a straight line, but a point on the outer rim traces a looping, bouncing curve known as a cycloid path. We can deconstruct this complex motion at any given point. We take the straightforward vector, the translation, and add it to the tangential circular vector, the rotation. The result is the actual instantaneous velocity of that specific particle. This is exactly why the point of contact on the ramp has 0 velocity. At the very bottom of the cylinder, the rotational vector is pointing straight backward, perfectly canceling out the forward translational vector. Meanwhile, at the very top of the cylinder, both the rotational and translational vectors point forward, adding together to create the fastest moving point on the entire object. The discrepancy we observed in the initial race is the direct result of this mathematical addition occurring simultaneously across every particle in the cylinder. By isolating and understanding pure translation and pure rotation, the complex, seemingly chaotic motion of any rigid body in the physical world can be precisely calculated and predicted.